All right, let's do it. Second last day of GPU. Can you believe it? Yeah. Next week is the last class for GPU. Yeah. And then after that we have regular parallel programming using OpenMP and AVX, which is actually going to be a blast. That is very different but considerably easier than the GPU part. So today is the last class where we cover technical material from GPU aspect. Next week we cover applications. Next week I'm going to show you a finite element application computed using GPU. So we're going to create a stiffness matrix. We're going to invert that system on the GPU, and then we're going to solve for the stress, etc., etc. But this week we have some things to talk about. I've been looking at your assignments. For your minor assignment, where we compute the flow through a network, you had two choices. You could use the Hardy-Cross method, which is an iterative method to solve for the flow rates through each section. The disadvantage being that when we use Hardy-Cross, we need to specify a flow rate in. And we can use that, and we need to specify the flow rates at all the exits. And then by balancing flow rates that we set at the beginning, we can move the mass around until we get a system which converges. That's Hardy-Cross. Newton-Raphson was the other method we could use. That one is a little bit harder because it requires us to invert a linear system of equations, the Jacobian. We have to invert the Jacobian matrix in order to calculate a vector of updates for us to calculate x. That is harder because I hadn't taught you how to invert that matrix, but the advantage of Newton-Raphson is Newton-Raphson allows us to deal with pressures, not flow rates. So in reality, thank you, Anne. They're working on the fountain. Lock it. Oh, Jose's coming. You could have locked it and just waved at him. Here it is. All right. In reality, pressures we know. In a pipe network, we have the pipes, we put them in the ground, we fill them with water. Then to push the water through the pipe network, we either have water coming down from a higher reservoir, so maybe a dam in the top of a mountain, or we pump water up to the top of a tank on the top of the building, or we use this kind of elevated system, or we use mechanical pumps to provide a pressure. We specify the pressure, and then the flow rate needs to be computed. So there is a difference because in real life, we never know what the flow rate is until we turn the pumps on. Then we measure the flow rate. But with Newton-Raphson, we're able to calculate what the flow rate will be before the pumps come on. With Hardy-Cross, we cannot. Now, there's a reason why I'm talking about this. Several comments. Most of you got, so in your minor assignment, there are two problems. The baby problem with those 5 pipes, that's a little one. Then there was a bigger problem, the bigger baby problem. Let's see, I gave you the solution to the small one. So there's no excuse for getting the wrong result for the small system. For the big system, I'd say 80% of you guys got the correct answer. A few people got the wrong answer. That's okay. I'm going to put my MATLAB solution for the larger problem online. So if you got the wrong answer, don't feel bad. I don't care. The assignment you gave me 2 weeks ago was just an update, just to keep me in line with what your progress is. So actually, I don't care if your answer was correct or not, but you should, because you need to make sure it's correct for the last minute. Speaking of last minute, many of you guys waited until the last minute to do this assignment. That is a very dangerous idea, because sometimes the assignment can be pretty hard, and you don't know how hard if you leave it until the last minute. You've been warned. Not a single group tried the Newton-Raphson method, which made me a little bit sad. Yeah, because for the next phase of your assignment, that Newton-Raphson method would be really handy. Here is your final system. So I know I was going to make everyone their own problem. Actually, I started to make everyone their own problem, and then I discovered that male ignorance on Newton-Raphson. Everyone used Hardy Cross. So I thought, tell you what, let's make a pipe network which is damn easy to solve using Newton-Raphson and hard to solve using Hardy Cross. So here we have a pipe system which is very hard to solve using Hardy Cross. I haven't specified any flow rates. It's your job to calculate the flow rates. All I know is that I have a source. The water source S is some height. Here I've written 100, but I might change that because our R values are fake. We have a water source, a water supply, which is higher. The rest of the network is at a height of 0. So the relative pressure up here is much greater than here. This height, this potential energy is going to drive the flow through this network. I want you to compute for me the flow rate at this exit and this exit, and all of the other pipes. You can't just tell me what these two are. You'll probably just say this plus this equals that. It does. unless some of the water is leaking somewhere. But tell me what EA and EB are. That is your mission for this. So I've updated the assignment. Now, using Newton-Raphson, you can solve this straight away. You don't have to do anything fancy. If you're going to do Hardy Cross, you have to do something a little bit trickier. With Hardy Cross, you need to assume a flow rate, then compute the pipe network, and then check to make sure that the pressure drop from here to here is 100 rho GH. So if the height here is 100, the pressure there is rho GH, right, from hydrostatics. Man, I'm not excited by the faces you guys are giving me. Do you remember fluid mechanics and thermodynamics? P equals rho GH. The pressure drop from here, and this pressure at the exit here is atmospheric pressure. So that if you add up the pressure drop from here, across here, across here, across here, and across here, that pressure drop must be rho GH. The pressure drop from here, 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 rho GH. The pressure drop across here, 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 here is 0. Yep, using these extra rules, you can check to see if your Hardy Cross method is right. So you've got two options here. Number one, keep using Hardy Cross and guess, and guess, and guess, and guess, and guess until you compute the flow rates you need. You can actually write a program to do this. You can. You just say, assume that the flow rate in is 1 cubic meter per second, and assume it all flows that way. And then compute the problem, and then compute the pressure drop. And if it's too low, increase the flow rate. And just keep going until the pressure drops agree. Fancy. Or you can use Newton-Raphson. Newton-Raphson requires inverse of the Jacobian. That's what we're going to look at today. You can use Hardy Cross to check to see your Newton-Raphson answer is correct. Your call, people. Yeah. So, the updated file will be online soon. I'm going to put it on there later. One final note, and I've updated the assignment to say this. You are submitting to me a professional engineering report, not a last-minute student report. I want to see a report that is like the report you would give your boss if you were working for the government. That means a title page with your name and student numbers, an index or table of contents, an introduction, the method, the results, a conclusion. Several of the people in this class, several of the groups gave me a good report for their mid-semester, for their update, for their progress report. That was excellent. Some people gave me, they didn't give me a report. It's like they took some rubbish and they emailed it to me somehow. You can do better. Give me a real professional engineering report. I want to see if you guys can do this, because this is something we need to train you to do. It's actually one of the goals of the system at NCKU. 30% of your final score will be off presentation. 30%. So if you give me rubbish, I'll give you rubbish. Let's do it. The linear system. All right. Here we have two equations. Are these equations linear? Yeah, they are. These are linear equations. How do we solve this? Well, it's pretty straightforward. Well, for a two-system equation like this, we can use substitution directly. If we're going to do it a little more generally, we can write this into a matrix. And then our solution is just going to be the inverse of this. So this is A, this is a solution vector X, and there's B. We have AX equals B. And if we want to solve for X, we can invert A and get B. Do we do this ever? No. We never ever do this. Now let me explain why. In most engineering problems we look at here, we're not playing games. We're solving unknown problems with millions of unknowns. We have a partial differential equation which we break up into a million pieces. We discretize using a million points. That means A is 1 million by 1 million. That's how big that matrix is. Now, 1 million by 1 million, that is 1 by 10 to the 6 that way, 1 by 10 to the 6 that way. How many potential elements do we have there? Yeah, 1 by 10 to the 12, right? Is that right? Now, you're probably thinking, in most engineering problems, that A matrix is what we call sparse. It's often diagonal, actually. So we might have a tridiagonal system, where we have a diagonal, two off diagonals, and zeros everywhere else. We normally do. Sweet. This might be sparse and might only contain about 10 million elements. But if this sucker is sparse, what is A negative 1? If A negative 1, if A is sparse, A negative 1 is the opposite of sparse. It is packed. It is full. 1 by 10 to the 12 elements. Do we have enough memory in the computers to solve that problem? No. Doesn't matter how many GPUs you've got, doesn't matter how good your computer is. Try opening MATLAB and calculating the inverse of a matrix that is 1 million by 1 million big. What does MATLAB tell you? It gives you a finger, doesn't it? It says, no. It says out of memory, normally. How do we solve that system then? It's important for us because a lot of problems use this idea. Hang on. Let's see if my pointer is even working today, because I don't like having to come back to the computer. Oh, is it? Oh, yeah. Oh. Here we are, yep. So, I've written an example for you there. A is a square matrix, n by n. X is a one-dimensional vector, B is a one-dimensional vector. Many engineering problems we write can be written in this form. In the non-linear cases, if we have a non-linear physics problem, like our Newton-Raphson, like our pipe flow problem, pipe flow is non-linear. We can't create an AX equals B system. Using Newton-Raphson, we can solve it, but using Newton-Raphson, we need to find the inverse of the Jacobian, which is still this. We still come back to this problem always. So we have AX equals B. That problem, the solution to those linear equations actually has applications in a large field of mechanical engineering problems and non-mechanical engineering problems. So Any nonlinear system using Newton-Raphson requires the inversion of the JDX equals R matrix, Jacobian matrix. All linear finite element solvers produce matrices. All distributed mass finite element solvers. If you don't know the difference between distributed mass and a lumped mass finite element method, then let me tell you, the thing you're probably thinking about is distributed mass. So you open up ANSYS or COMSOL or SolidWorks. Have you guys done FEA in SolidWorks before? Don't trust the answer. But SolidWorks can do FEA if you load it up. That is an AX equals B system. So every time you fire up SolidWorks or ANSYS to calculate a stress, AX equals B, that's what we're solving. Incompressible Navier-Stokes also relies upon the solution to an AX equals B problem. Compressible Navier-Stokes can avoid it. That's one of the reasons actually I enjoy doing compressible Navier-Stokes, because you don't need to solve AX equals B system if you want to do compressible flow. But incompressible, it can't be avoided. Also, steady. Any steady method without the use of the fractional step method, which you're probably not familiar with, requires a solution to an AX equals B system. So, let me tell you, 99% of the calculation your professors are doing requires this solution. Solution to the AX equals B system. I'm not sure if it's this or this or this. So, if we have a matrix A, theoretically we can solve for X by inverting the sucker. Like this. If we want to calculate the inverse of that matrix, actually there are a lot of things we can do. We can do Gaussian elimination. Remember that game? When you guys first started learning mathematics, your teacher showed you the matrices and then you solve, you put the identity matrix here and this here and you do, and you get your inverse. That sucks. Computers don't like doing this either. It can't be done in parallel. The solution is a sequential problem. We can't solve that inverse in parallel. So that's horrible, because if we have a million by a million matrix that we have to solve sequentially, it's not feasible. Plus, a million by a million gives us 1 by 10 to the 12 non-zero elements for a sparse matrix. I guarantee you, A is sparse, then its inverse is full. We just don't have enough memory. So, for large values of n, where n is the size of the matrix, this calculation can be difficult and very time consuming. It really can be. One time a company asked me to help them compute the inverse of a matrix that was 120 million by 120 million. I'm serious. The A matrix was 120 million times 120 million. And they wanted me to invert that. They didn't have enough money. I sent them away. We don't. We never compute the inverse of A. We have to find a way to solve for A without computing its inverse. Have we done that before in this class? Everyone should be going, yes. We have actually. Yep, several times. When we used red over black SOR. When we used red-black SOR, we were solving an AX equals B system, and we weren't calculating the inverse of A. Now, we were very, very fortunate, because the problem we were solving, which was a 2D Poisson equation, that is a baby equation. That's like you learn to walk, you start eating solid food, you learn to write ABC, and then you solve the Poisson equation using red-black SOR. It's simple. Because that matrix is diagonally dominant, we can solve using SOR. What the people who do SOR don't tell you is that if that matrix is not sufficiently diagonally dominant, then SOR diverges. So you can't use SOR for every matrix. You can't use Jacobi for every matrix. It is only suitable for a small range of problems. Fortunately for us, many finite element problems are diagonally dominant. Many heat transfer problems are. But if you want to invert our Jacobian matrix, it is not diagonally dominant. Jacobian matrices are most often the exact opposite of diagonally dominant. Jacobian matrices often have 0 on the diagonals. Now, if you have a 0 on the diagonal, this is a part where you guys try to remember what the equation is for SOR. There it is. That's the SOR equation. If you have a 0 on the diagonal, there's the diagonal. What happens in a computer when you divide by 0? I swear, actually, there should be a special symbol that the computer gives you when it wants to give you this. In a computer, it does this. One of those. Hopefully, every single person in this classroom has seen some of those before. I know you have. I designed this course to make sure that you get a chance to see these things, because often this one is returned as -1. Have you guys seen that before? Any one of those. You know, if you run a simulation and you look at that results file and you see NAN, that is a bad thing. And I'm glad that you guys have had a chance to have some exposure to not numbers and not defines. If we have a a 0 diagonal, SOR falls to pieces. Jacobians have 0 diagonals. Trust me on this. Now, you can reorder the matrix, but reordering the matrix requires some heuristic or intelligent algorithm. So no, we're not going to do that. That's too much trouble. So what are we going to do? Well, let's have a look. Red-black SOR, we can use it for Poisson, but we can't use it where 0 occupies a diagonal or when A is not strongly diagonally dominant. Most of the time it is not. So we need to find a different way. We're going to use CG. CG is a Krylov subspace method. Now what that actually means is that the mathematics is too complicated for you guys to understand. Don't fear. The algorithm is very simple. I'm going to give you the algorithm. I'm going to give you several codes. All you guys need to do is fill in the blanks. Conjugate gradient method is related to the method of, or gradient descent. That's basically where we compute solutions based on the gradient of the solution at any point in time based on a guess of the solution. Has a lot to do with Newton-Raphson actually in some ways, but CG is just simply put a very smart way of solving for a linear system. It is iterative, which means we do not calculate the inverse of A. We create a guess of X, then based on that X, we calculate a vector of directions that we can improve our estimate of X on, and we keep improving X until we get our solution. The good thing about CG is it is all the same kind of operation. It is all matrix vector operations and dot products. You guys are experts on dot products on the GPU now. You're all experts on performing vector multiplications on the GPU. On the GPU, when we want to perform our dot product, we take two vectors and we multiply each element. Then we have to sum them using parallel reduction or atomic operations. If you use atomic operations, I'll execute you. So you're not going to do that. You guys are going to use parallel reduction. Everyone here should have a working parallel reduction code from last week. So half of CG is finished already. The only part you need to know now is how the algorithm works, but that's easy, and then the matrix vector part. This is the part where I say, I quit, and then remember I already quit. Yay, all right, we're good. We're rocking and rolling. What makes CG so great is that theoretically, if you have an n by n matrix, CG will iterate to the correct solution in n steps. Now, mathematically speaking, you don't understand what a frickin' miracle that is. If you double the size of your A matrix, quadruple the number of elements, you're still only doubling the time it takes to solve the problem. Most of the time when we look at mathematics operations regarding matrices, it is not a linear operation. It actually goes with some power of n. So CG is a very, very powerful tool. But it doesn't work. If you have an n by n matrix that you need to solve for, and you take n steps, you won't get the exact correct answer because the computer has rounding errors. We only use single precision. If we only use single precision, we can only hold so many numbers, about 28 numbers. In those 28 numbers, well, sorry, that's 28 bits, my apologies. So not 28 numbers, 28 bits. We hold that result in 28 bits and we use the other bits for sign and for the power. When we perform our operations on these with this precision, we lose accuracy and we actually need slightly more than n operations to solve our problem. What does this mean? This means that actually using CG will get you, in the very worst case, same performance as SOR with omega equals 1.5, and most of the other cases better performance. Only a few other methods go faster than CG to my knowledge, and they are all harder to do on the GPU. To my knowledge, around Taiwan, 6 students have got their master's degree by putting CG on GPU. Just that. So they basically show what I'm going to show you, put it in a thesis, and then they graduate and then they run away as fast as they can. Because it's already been done 6 times, you guys can't do it again. Yeah? No way, man. No. I hope you know what you got yourself into. If you can derive a better method, an improved conjugate gradient scheme, then you have the potential to get a Fields Medal and you'll get a PhD. Then you'll be rich. But
I have a question.
Yeah.
How can you said there are methods that can do it in less than n steps? Because if you have
yeah.
means you have n,
Yeah.
n number of variables.
Yeah.
How can you do less operations than the number of variables that you have?
It's magic. We change the space. So we shift out of the n by n conventional space into a higher space, solve the problem in higher space, and then come back down. Yeah, that's why don't try to read about the method in mathematics journals. It's pretty freaky. It's pretty terrifying, actually. The disadvantage with using CG is that it only works for symmetrical A matrices, but never fear. Because Jacobian matrices, like the one in your assignment, they are not symmetric. So we have to find another way to solve them. There are other schemes which are derived from CG, BiCG stab. They are both similar methods. They both use matrix, vector, and vector-vector operations. And they can be applied to non-symmetric matrices. So today I'm going to show you CG. You can modify it to get BiCG stab pretty easily. Should only take you a few minutes, or maybe half an hour. And then after that, you can apply it to nonlinear problems, which is pretty cool. Come on. Now, some things you're probably already familiar with. The concept of a residual. If you have an AX equals B system, we have AX equals B. If we have the correct solution, if X is our correct solution, then if we write B minus AX, since AX equals B, that's going to be 0. But if X is not the correct solution, then we're going to get a residual R. This is the correct way to compute the residual. So when we actually solving any physical problem, if we really want to compute the residual, the best way is to substitute our estimate for X back into the governing equations, calculate AX, subtract it away from B, our right-hand side, and calculate R. And we never actually use R. It's always sum of residual squared, which is a dot product. You can see that, right? I can see it. Otherwise, the sum of residuals might be 0, but you'll still have the wrong answer because some will be negative, some will be positive. So If we want to solve CG, we need a definition for residual. There it is. R equals B minus AX. Our mission is to solve for X such that B minus AX equals 0. And we're going to iterate X such that we get the correct result. All right. I think I just told you this. If we want to measure how close we are to the correct value, the problem is that R is a vector. So which R do we look at? I mean, we can't just pick some values of that vector out. We need to find a way of measuring how close the system is. So we normally sum the squares. Summing the squares of that vector is basically taking its transpose, multiplying by itself. That's just a dot product. So we take the dot product of the R matrix against itself. So we can use our parallel reduction code straight away to perform this computation, which is very handy for us. In GPU, if we want to do this using many blocks and many threads per block, that means if we have m blocks that we need to add m values after we've performed our reduction. Just keep that in mind because we're going to need to do it. Theoretically, this will be 0 as we approach our solution. How close do we have to be for our solution to be good? Not that close. For a 2D heat transfer problem, for example, our sum of residual squared using a 25 by 25 problem, that's 625 unknowns. That's a matrix 625 by 625 in size. If RTR is 30, we are pretty close to the answer. Now, most of the time when you guys are using answers to try to iterate to a solution, your professors will tell you to try to converge on 1 by 10 to negative 6. That is arbitrarily small. First of all, you have to understand what that residual, that ANSYS is using means. Most of the time, if you're approaching 1, then it's probably good enough. You're probably on to a solution. The danger is that you might be on a local solution. Let's not talk about that one. So we need this RTR. I need a holiday. Come on. We need RTR to solve our CG problem. So we're going to solve CG using a collection of matrix, vector, and vector-vector operations. That's a dot product. Since we have already done parallel reduction, the only thing we really need to do is a matrix vector. But before I go too deep into that, let's talk about how it actually works. CG is actually made up of a collection of a number of steps. I can't remember how many, 9 steps? Let's talk about each one. Actually, there are a lot of intermediate variables that we need. Well, normally, when we're solving a system like this, we need to come up with an initial guess. If you had to make an initial guess of how much money is in my bank account, what would you start with? 0. Thank you, Jose. That's the way to go. You're my favorite student. We're going to set our guess to 0. We're going to set all of our x as our solution vector. It is an array containing n elements. Set them all to 0. Then in the first step, when we calculate r, what is r? Well, let's see. R is equal to b minus ax, but x is 0, which makes r equal to b. There's a good reason for setting x equal to 0. That makes our residual computation at the beginning very, very simple. The residual vector is just b at the beginning. So r is equal to b when x is equal to 0. We have another intermediate array. Oh, this is a array, yeah? P, sorry. And we set that to b at the same time, also because x is 0. After we've set p, r, and x, we can start iterating. So any CG method, we need to pick x first, which is 0, r, which is b, p, which is b. Then we can start iterating. We keep iterating until either the maximum number of iterations has been reached or the sum of residual squared RTR is less than 1. Pretty good guess. Wind. In Taiwan, I have to think, is it an earthquake or is it just the wind? I have to stop and feel. Let's do the iteration. So step 1 here is just a warm up. 这是加热，我们加热的工作。The next steps are the iterative steps. Step 2, we calculate an intermediate called AP. A is our A matrix. A 会改变吗？问你们，作为我们的话，那个 A 会改变吗？平常不会。如果那个问题是 nonlinear，A 会改变。 But for us, all of our finite elements are linear finite elements. A doesn't change. For your Newton-Raphson, J changes. So that will be updated. A equals A times P. So that is a matrix vector operation. Once we have that vector AP, we can compute PTAPP. Remember at the start is just R. P transpose just means we're just changing the dimension so we can multiply out properly. That's all we're doing here, so that's what we get. P, AP. Well, let's see. AP is a vector. That's a vector. So PTAP, that is a dot product. So that's matrix vector. This is a dot product. That gives us a scalar, just one number. We have to store that one number on the GPU. Remember that. Then we have RTR. That's our residual. That's a dot product. We can do these at the same time because this RTR and PTAP are not connected. So when we do our dot product code, we can actually perform two dot products in the same kernel. Don't forget that step. Number 5, we compute alpha, which is the ratio of RTR and PTAP. When this alpha is very small, we know we're getting to our correct solution. And we must, because RTR 越来越小, alpha 越来越小. Once we've got the correct alphas, we can update our solution. Our 新的 x 就是旧的 x plus alpha times p. Alpha is a scalar. So this is a scalar operation on a vector. That is what we did in the very first GPU class. That is the easiest code. So I don't need to talk too hard about that because that naga henjindana. Then we do this one, R star. Then we need to calculate R star T, R star. That gives us a scalar. Then we calculate beta. Beta is just the fraction of R star T, R star divided by RTR. This computation here, well, what is that? What is R star? AX take away B, R star, and this uses a new X, see that? It's the new residual. So beta is just the ratio of the residuals. The new residual versus the old residual. When this is equal to 1, we should be, hopefully we're done. Yeah, we should be pretty ready to go. Then we all update P. Now, let's review these operations. Alpha equals RTR divided by PTAP. 这个是 parallel or sequential? Is this, can we parallelize this? It's just one number divided by another number. We don't need to parallelize this. This one here, embarrassingly parallel. This one here is a matrix vector, take away a vector. That's pretty easy. Then we have another vector-vector scalar operation. So let's break down the operations. So we set x. When I say x equals 0, I mean that is actually a vector containing zeros. P is equal to R is equal to B. Then we iterate. Here I say RTR is less than 1 by then -5. 那个你们可以自己随便选. You pick your own and live with the consequence. Calculate AP first. AP is a matrix vector operation. It is 100% parallel efficient. Then we calculate PTAP. That is a dot product. That means it sucks. And there's nothing we can do. Then we calculate RTR. Another dot product. Compute these at the same time in the same kernel, please. Then we calculate alpha. That is a scalar operation. Just one number divided by one number. There's no vectors, there's no arrays. There's just one value. You can actually do this in the same kernel you do this in. Have every thread compute the same alpha, and then update x. This is a scalar operation on a vector. That is 100% parallel. Then you got this one. That is a matrix vector operation, but we're going to find a way to improve this because even though matrix vector operations are 100% efficient, there are better ways that we can solve for that. Calculate RTR for the new residuals. Calculate the ratio of the old residuals to the new residuals and update P. And then we just keep going. That's our algorithm. That's CG. It is a beautiful method. and very, very powerful. We can actually use alpha to update our residuals. The new residual vector is the old one, take away alpha AP. We already have computed AP, we already have R, we just computed alpha. So you can see here, we actually compute alpha here. So once we have this, we have AP, we have R from the previous iteration, we can update R star using the old R. But then we have to update R at the end of it. Oh, don't forget that step. We have to set R equal to R star at the end. Oh, so how do we make this work? You know, I love MATLAB because coding in MATLAB is just so easy. And MATLAB 跟 CUDA 完全不一样，跟 GPU 完全不一样。MATLAB 有一个嘴巴 and when there's an error, it goes ding. Oh, funnel. I hear that noise too much. But MATLAB's great because it can do the inverse of a matrix easily if it's small enough. So if we are going to write a GPU code that solved for an AX equals B system, it seems like a sensible idea to put our AX equals B system into MATLAB, then check to make sure our X is correct. First calculate X in MATLAB, then use our CG solver in GPU to check to see if they get the same results. Now, if we want to do this, then we need to pick an A matrix which is symmetrical and positive definite. You guys don't need to worry about what that means. This is an A matrix which is positive definite and symmetric. You can see it's symmetric. What a beautiful symmetric matrix that is. And we've got a very carefully selected B vector here. That's a joke. 1, 2, 3, 4. Come on, people. I could have just picked 1, 1, 1, 1, but that's boring. So I have a B, I have A. If I want to solve this in MATLAB, what am I going to do? I could type inv A times X and get my answer. Do it. Do that first. Get what the X is. Then take my MATLAB code. This is a picture in the notes which aren't online yet, but that's okay. Have you found the MATLAB code for CG on the wiki page? I know you have. I can see it right there. Yeah. Just Google CG wiki. Enter. Go to the web page. Steal their MATLAB code, which is my MATLAB code, but I didn't put it on there. Grab it. Open up MATLAB. Save it. Run it. And you can see all of the steps which I talked about are right here. AP equals A times P. Alpha. X. R. RS new is equal to R dash times R because I'm updating R using this method here. If I'm less than my residual, break. Update P. Save over R. Every step that you need is right there. If you wanted to write a GPU code that did this, you can copy that. Or you can copy my CUDA code, which is coming up. Now when you run this, the very first thing you guys are going to do first, INV of A times X, calculate the real answer. Then check your CG code to see if it works. The good thing about having a CG code is that in MATLAB, if you know the A matrix and you know the B vector, if you have a MATLAB CG code, that means that at every iteration you can print out the values of alpha, beta, RTR, P. All of these parts that are used to solve CG, you can print out at the MATLAB command prompt. That way when you start debugging your CUDA code, because I'll give you a surprise, your first CUDA code is not going to work. Julie Mayo Iguren. Not even me. When I write my CG code the first time, it never works because it is a complicated calculation with many steps. There is going to be a bug somewhere. If there is no bug and you think you got the answer right, that's actually a serious problem because that means your bug is actually quite difficult to find. They're the worst bugs. If that happens to you, call me straight away so that I can sit down, look at your code and help you figure that out. So, everyone's clear. I'll see 20 MATLAB CG codes today before the end of the class. Everyone here is going to have a reason to write a CG code in MATLAB to help them debug their CUDA code. And before you create a CUDA code, you guys are going to write a C, C++ code, right? I hope so. Before we start making this work on GPU, what do we think about? Well, let's see. When we run an application on GPU, we need to think about what variables we need to allocate in memory. So, because we need to use CUDA-malloc to prepare those variables. Here we have some special things because most of our computations in CUDA are done on arrays, 1D arrays. That's the way we normally do it. But today, we have some important scalars, single values. You have two options. You can create 5 arrays of single elements if you want it, or you can create a small array with 5 elements, and inside that array are our scalars that we need. The code that I'm about to show you today uses this idea. We create an array holding 5 elements, and our important scalars are held in that array. The important scalars we need are RTR, RTR new, PTAP, alpha, beta. The 1D arrays we require, B, AX equals BB, X is our new solution, X, our solution, X. Residual, P, app. There are 5 of those, all of those have length n because they're one dimension. We only have one 2D matrix, A. That's n by n. Normally A is sparse. Normally, because A is sparse, we would store the non-zero elements. Fun silly. I'm not going to ask you guys to do that today. Store the whole damn matrix. Store all the zeros. Get CG doing some 0-0 computations. It won't matter. But in the future, when your professor gives you a linear system to solve, or if you're doing some finite element calculation to calculate stress, or you have a steady heat transfer problem to solve and you've got that large matrix, you're probably going to need to use some kind of compaction method like CSR to remove the zeros from that A matrix, because we don't need them. 0 times anything is 0. And we don't divide here by 0, so that's good. So we create a small array of floats to hold those 5 scalar values. The rest are 1D arrays. Our A matrix is n by n. Does that mean we use a 2D matrix in MATLAB? In CUDA, sorry? Has anyone here Googled CUDA 2D matrix? Have you guys seen what people write on Stack Overflow when they ask, how do you create a 2D matrix in CUDA? All of the experts come back and say, you don't. If you have a 2D matrix of dimension n by n, you create a 1D array of length n squared. Google it. Go to Stack Overflow and see what they say. I promise you this is what they say. Because creating a 2D matrix on CUDA is a stupid idea. Don't do it. So our A matrix will be held in a one-dimensional array of length n times n. Is it raining? No, not yet. It's just, the sound of nature and that ambulance. Allocate memory is going to look like this. Look at this beautiful code that I'm giving you guys. Take a picture. Because I haven't put these notes up yet, and this is what we call improvising. 先拍照. He's already got his CG code ready. Cut and paste, baby. There's nothing magical here. Everyone here already knows how to use CUDA-malloc and malloc. All I'm doing is providing you a checklist because there are a lot of variables we need in CG to make work. If you're missing one, it will be a pain in the neck. A, dA, bxr, and our magical solution h scalars. Thank God I picked a good name to store those things in instead of picking a crap variable name. This is a way of me to remind you, when you write CUDA code, make sure your variables have sensible names. And the rest of them. B, X, R. You can see, here's P. P is a vector. Did I allocate HP? Nope. I don't need to because I don't perform the calculation on the host. P is only used as part of the CG computation, so we only allocate memory for that on the device. In fact, the only thing we do, we set up A on the host, so we need to set HA. I've got HX here. HX is basically to store our solution in. HR is damn useful if we want to copy the residual back, because that's pretty useful for debugging. B is an initial condition. All the rest are on the device. So let's see. Let's talk about what we've already done. To calculate RTR, PTAP, we need a dot product. Everyone here has a dot product code. That's green for done. Then X, 新的 X 就是旧的 X plus alpha times P. Wasn't P, can't remember what it was. That is an embarrassingly parallel scalar vector operation. We already know how to do that one. Matrix vector computation on the GPU is something we have not done yet. But how hard could it be? Not very hard. Let's do it. Simply put, this is our plan. It's a good plan. In our GPU, how many threads do we want to use in total? The answer is as many as we can. We want to use a lot of threads. Now, when we solve engineering problems, how big is our A matrix? Here is our A matrix. Here I've color coded it. Our A matrix is normally huge. In most engineering problems we'll be doing in this class, we're only mucking around here because we're practicing, but in reality, your A matrix will be 1,000,000 by 1,000,000 easily, for any real problem. So how are we going to do this in parallel? It's quite easy actually. We have one CUDA thread manage one row of our A matrix. So thread 0 is going to go through our matrix and times this and this and this plus this and this plus this. This is a sequential operation, right? Because we're summing the multiples of this. It's like one massive fat dot product. But because we have one thread doing it, it's okay. We don't need to use parallel reduction here. That's a stupid idea because it's not parallel efficient. What we can do is we can create, if we have an n by n matrix, we create n threads. And then each thread goes through its entire row, multiplies by AX, and produces this single value. That means two things. One, 我们可以非常的公平分享这个工作，用平行计算的话，如果我们有 n by n， 我们用 n 个 threads 的话，这个是 embarrassingly parallel. It's very nice. Second, thread 1 will access this row and save its data here. Thread 2 will do this row and save its data here. Do we have data racing here? No, because each thread has its own destination location. So it's true, we are trying to overwrite the vector, the result vector at the same time, but never the same point in memory. So it's not data racing. So by breaking it down into this, we can take our n by n matrix, allocate n threads to do the operation, have our n threads perform n operations. It is a very handy, neat little idea because each thread does quite a lot of work, but it is memory bound. That's the only downer. So each thread is going to occupy itself by multiplying one row against that solution variable, that vector there. So n operations to produce that single value. And then we're done. Your code's going to look something like this. So if you wanted to write a simple code to write GPU on, here it is. In main, you'll see I haven't put the include stdio.h up the top because, come on, you guys have been here a long time now. 我应该不用放那个 include stdio.h at the top 吧？你们现在都很熟吧？ First, we allocate memory. I already showed you allocate memory. Init. This function init, 它的工作就是 calculate A, calculate B. We have to solve an AX equals B matrix. That means our very first step is we need to create this matrix. In this class, most of the time I'll give you the A matrix, but today's tutorial you'll have to create your own. It's easy. After we've created our A matrix, we need to send our A matrix and B matrix to the GPU. We don't need to send X. Ask me why. Because X is 0. We can set the memory on X to be 0 on the device straight away, so we don't need to copy X. If you really want to, you can set X to be equal to 0 in init and then copy X over, but you're just copying zeros. That's up to you. Then, set up CG. Set up CG is basically a simple operation where we set B on the device, we take B. What do we set R equal to at the beginning? B. P is equal to B. N is our size. So that set up CG parallel kernel is just this. We calculate the element we're working on, and if I is less than or equal to N, we set R and P to be both equal to B. That's a pretty straightforward parallel operation, right? We do this in parallel because it makes it easier for us. Is there any other way we could do this? Yeah, CUDA memcopy. We're going to use CUDA memcopy device to device. We don't need to do this. Your call. I'm showing you that you can do this, but in reality, you just use CUDA memcopy. I'll write the code down. CUDA memcopy, the first argument is the source or the destination? It is the destination. We want to copy over R. The source is going to be B. Then the size. Last argument. That's it. You can do the same thing for P, which also needs to be copied. And then you're cooking with gas. That's so much faster. There's only one reason I show you this and then do this, so that you guys can see they are the same thing. Do that. Take a picture. You might need to get closer to take a picture to actually see what is happening in there. I will put this online tonight or tomorrow, but you need it this afternoon, so you'll need to rely on your picture. I'll leave it up during the tutorial as well. All right, let's talk about what you see here. You know what I see here? the same MATLAB code that you guys are going to steal from Wiki. It is the same thing. Calculate AP. To calculate AP, we're going to perform a matrix vector product. Jiga function share. That's your main job today. You only really have one difficult job today. That's that. And it's not even a difficult job. So you're going to write a code that performs a matrix vector computation and test it. After you've got that working, that matrix vector product will produce what AP. There it is. It takes A, takes P, gives you DAP. Once I've got AP, I can compute PTAP, PTAP. PTAP is a dot product. You guys wrote that code last week. So you've already got that one. And that is going to compute the dot product of DP and DAP. DTemp. What the hell is DTemp? Let's think hard about this. When we perform this dot product, we've got blocks per grid and threads per block. When we perform this dot product, we're still going to have this many blocks per grid results, right? Each block of threads is going to come up with a single number when we perform our reduction. We need to add those together and store the result. I store the array of those results into dtemp. Then I use a special function called sum and store, which goes over this array using a single thread and a single block to add the elements together. So you can see here, this is done in parallel, but sum and store is one thread, one block. I take temp, I'm going to save it somewhere into scalars. Dscalars is my array of 5 scalar results. Where do I save it? In the second element. That's what that number 2 is for. Then RTR. RTR is also a dot product. I can put these together. You guys are going to put them together. Otherwise, we're wasting time here. Perform our dot product to calculate RTR. We're going to store it in the 0th element. Then we update X, that's a parallel computation. Update R, that's a parallel computation. Another damn dot product. It's all dot products. Once we've got that, what is the dot product that we're computing here? Isn't it the new R? It is. dr. We're calculating the sum of residual squares. And we're going to save that in the first element, not the 0th element, the number 1 inside scalars. Once we've got that, we can update P, and then we copy everything back. That's CG, cooking with gas. Your code should look exactly like this. The only thing you really need to write now is that, and maybe you should have written a function like this last week. So you can just cut and paste that one. This guy from the first week that we did GPU, that's pretty straightforward. So your work today will be doing this one. Using the information I've given you, you should be able to use CG to solve any symmetric linear system. Which linear system will you solve first? This linear system. You guys are going to write your CG code, then using a single thread and a single block, use CG to solve for the inverse of that AX equals B system. You know what the answer is. Come on, computer. There's the answer. If your CG gives you this, good work. If it doesn't, that's a bad thing, because I know MATLAB doesn't make mistakes. Come on. All right. After this, we can also use it to solve finite volume problems. Now, development strategies. Today's code is probably going to be the most complex single algorithm you've written on GPU. The CG class in this course is easily the most fun class that we have in the semester. Because when we write this CG code, you saw how many kernel codes we have there. There are a lot of ways we can make mistakes writing this code. So with 20 students in this class, I'm expecting to see every kind of bug that I can see before 5 o'clock, I reckon. My advice. This is just advice. So you can start right now if you like. Whenever you write anything complicated in GPU, don't just write one massive fat code and then after you finish the whole code, try to compile and run it. The bigger a code is, the higher the potential for bugs. So, while the code is small, compile and run it. Then once you've ascertained that that small section of code contains no bugs, you can move on. But we have a strategy for this. It's not just a matter of overwriting the code. So this is my advice. To complete today's task before 5 p.m., and you guys are going to finish before 5 p.m. because I'm having a going away dinner for my visiting foreign student, and I'm going to kick you out of this room at 5 o'clock. We're going to break this down into 2 phases. This is just advice, so you don't have to do this. But my advice is you break it down into testing and implementation. 2 discrete phases. You do a little bit of coding, then you test to make sure the coding works. Today, your testing should be basically testing your dot products work, testing your scalar operations on vectors work, testing to make sure your matrix vector multiplication works, testing to make sure your memory allocation works, testing to make sure that you're not creating any problems on my GPU. I know that one person is. I've got their username. So, you're going to perform these in discrete blocks. You're not just going to do one massive fat chunk of doing and then spend all afternoon debugging. You will go insane today if you try to write one code and just try to debug it. Because I promise you the potential for problems in developing a CG solver on GPU are huge. So, my advice. I'm not going to tell you how to solve the problem. It's up to you. But my advice is write a small code. Compile it. Check the result when you run it. Use CUDA memcheck. If CUDA memcheck says OK and your computed result is correct, so when you write this code, you're going to test your matrix vector multiply. Use your hand or MATLAB to check the result of the matrix vector multiply first. Then you know what the answer is. Then you write the code, you run it. If it's correct and CUDA memcheck it says everything is fine, save it. Then make a copy of it somewhere else. Then in the next phase, do not use the first copy. Use the new copy in that location. And then you start to add things on that code. Maybe you will find that in the next step, you'll create a bug in that code that is so strong that you can't save that code. But that's okay, you can delete that code and go back to the first one you saved. Sometimes when we're doing coding like this, if you don't have those discrete files saved somewhere else, you can really stuff yourself up because you can create a bug so complex that you can't fix it. And then you lose the whole code. We normally use revision control software for this kind of thing, like Git. We don't need to use Git today. Usually, you guys are going to do it manually. Make copies of each code that is able to do certain tasks. So my advice, write a code that allocates and frees RAM. Don't just test the memory allocation code before you test the freeing code. I feel embarrassed that I actually have to say that, but every time you write CUDA malloc, you should be writing CUDA free underneath somewhere. Straight away. This is something you need to do together. Then when that's right, check your dot product code. You already have a dot product code and you already have an allocation code. So you should be able to start this straight away. Matrix vector multiplication code. Write a separate function that performs a matrix vector multiplication. Then import a matrix, import a vector. Do the single matrix vector multiplication. Check the damn result. Then when everything is right, save it in another place. Then try your CG code. Once you've got all of those things working, you should be able to try CG and make it work. You're going to try then using CG on the 4x4 matrix I gave you then. Then after that, you're ready for something serious. Come on. So, at the end of this class, you're going to have a working CG code. We're going to talk about this one now. Inside your account on my supercomputer, I should be able to go into your user account and see lots of different folders from today that show me how you've created different copies of your file as you've developed this thing. That means that if you ask me for help on the odd chance, I can help you go back through those codes and help you identify where you made the bug. Remember, take small steps. If I see one person just blindly copying out one massive fat code, I'm going to break his fingers or her fingers. Let's do the tutorial. Your mission today is to solve a steady heat transfer problem. This is an easy problem. We have a 1D bar. The left temperature is 0, the right temperature is 1. I want you to find the steady solution. Why did I pick this problem? Because I know the analytical solution. T equals X. If L is equal to 1, and T is equal to 0 there, and T is equal to 1, in the steady solution, T is going to linearly vary from 0 to 1 across that 1. So T is equal to X. I don't even need a computer to solve this problem. I know what the answer is. 所以这里应该没有一个人会问我，嘿，老师，我的 CG 的结果是对的吗？ Did you get X? Because if you didn't get X, it's wrong. You have the answer. We need to make an A matrix. So, create the correct A matrix. I'll do it here. It's not rocket science. Let's see. Governing equation, which you guys should have memorized by now. Oh, it's not there. 剪刀石头布. Write the governing partial differential equation for steady heat transfer. Anyone can help him. Hey, you're at a computer, wiki it. 1D. 1D, man. 1D. Where? Okay. Go down, go down, go down. Wait, stop. That's 0. It's that. Trust me.
Only this.
Just that, yep. Yeah, that's it. Write it down for me. Yeah, sure we can. Oh. You haven't used what before? Huh? Git. Oh, it's pretty good. Yeah, revision. It's more automatic than the manual system I'm making everyone do today. You can. You set up a server. Yeah. But it doesn't have to be that special.
No.
Yeah, just a box. Yeah. Come on. Are you ready? Come write the governing differential equation down for me. Anywhere. Up the top or here. Huh? No, just the PDE. Yeah, just the PDE. Yeah, well, that was all right. The partial's fine. Oh, okay. Old school. Kỹ用 X 就. I wish I had a vending machine with beer in it in this room. That's it. Yep. Yeah, that's it, man. Thank you. Bye. Let's see. The discrete form of that is that. But we multiply the dx's by that dx squared by 0. It's gone. So we have this. That is the general stencil. For our problem, on the left-hand side, we have a temperature equal to 0. On the right-hand side, we have temperature equal to 1. So we have 1 and n there, which means at the endpoints, our equation is going to be a little bit different. At the left end, with I equals 1, Ti minus 1 is outside of our simulation boundary, and that is equal to 0. So we just have that. We have Ti plus 1 minus 2 Ti equals 0. Right end. What do we have? The right end, we have Ti plus 1 equals to 1. So we have this replaced with 1, but the other two are still there. So I'm going to move that one across the other side. Which is fine. For all the other points, we have that. Our matrix is in this. Are we ready? 0, 0, 0, 0, negative 1 at the end. That's B. Our A matrix. Let's see, at the left end, we're talking about the first T here. Nothing to the left. We have negative 2, then 1, then 0, 0, zeros all the way. At the right end, we've got 1 and negative 2 on the diagonal. Oh, whoops, sorry, my bad. And 0, 0, 0 everywhere else. And then on the diagonal, for all of the other points, that's our matrix. Now for a 4 by 4. Have I made a mistake yet? Because I'm just doing this off the top of my head. I don't memorize this stuff before I come to class. Of course you can. And then, yeah. Yeah, just multiply the whole thing by negative 1. Yeah, it's the same thing. If we had a 4 by 4 system, can someone compute that in MATLAB for me, please? What is T? Yep. Hey, sit down first, we're not done yet. Everyone should have already confirmed that's our T result. Rugal Wamiyo, we get n by n. You should be able to make your own damn A matrix. Now before we get going, before I let you go on this, if we have a 2D heat transfer problem, will our A matrix be non-symmetrical?这个是一个 1D heat transfer 的问题，所以我们的 A matrix 其实要做的话很简单。如果我们有一个 2D heat transfer， 我们的 A matrix 是 symmetrical 还是 not symmetrical? It is symmetrical. Most linear problems in engineering produce symmetrical matrices, even for non-symmetrical geometry. So if I had a 2D heat transfer problem that looks something like this. And I set this temperature here to be 0 and this temperature here to be 1. And I set Newman conditions on all the other boundaries. You can see this is not a symmetrical solution. The A matrix will still be symmetrical. That's a very interesting property of most positive engineering problems we work on. In this class, all of the real engineering modeling problems we work on will give us a symmetrical A, so we can use CG. On the exam, at the end of the semester, I'm going to ask you to make an A matrix for an engineering problem. Oh no, it'll be fine. It will be a symmetric matrix. If the symmetric matrix you compute is not symmetric, you have a big problem. So, I fully expect you to be able to create an A matrix for a 2D problem. Today's example is for a 1D. Don't let that stop you though. At the end of today's class, once you've finished with this 1D test, you can use your CG code to simulate a 2D problem. Your call. My advice would be for you to solve this. We've already done this before. A square region with t equals 1 here and t equals 0 on all the other edges. Contours of t look like this. We do this because we have an analytical solution to the problem. We can use Fourier series to solve this analytically. If you're interested in the analytical solution, I can give it to you. Didn't we use this in the first week? Yeah, I did. I gave you a code that solved this in the first week of the lectures. So if you want to do a 2D problem after this, be my guest. If you want to work on your assignment after you've finished getting CG working for the 1D case, yeah, okay, 但是你的 assignment 是要 by CG or by CG stab. So you have two options today. After the 1D case works and you've shown me your result and your CG code works, you can actually either use CG to solve this 2D problem, or you can use your CG code to modify to create a by CG stab or a by CG code. All of the information about CG, by CG stab is on Wiki. Shouldn't be too hard to modify your codes to reproduce that. Then you can use your by CG stab or by CG to test your 1D solution. It should still provide you the same answer. That's it. Let me go back to this slide. You guys all know what you need to do. This, using, what dimension did I say? Did I give you guys a dimension on today's tutorial? No. 100. Use 100 elements. That means your matrix will be 100 by 100. That's about a good number. Good luck. And I'll leave this up here. Remember, my advice is to put the PTAP and the RTR calculation together. Update X, update R can also be together in the same kernel. Have fun.